Section 11.1 is about orthogonal functions. Thank you for joining us. First thing I want to review is the inner or the dot product. So we're going to do this for about 2 minutes, and then we're going to be over vectors. So remember, this is normally how you see the inner or the dot product. Have you also seen another way to write this? Or is that the only way you've ever seen the dot product? Only seen it that way? Another way is like this. So that's the notation we're going to use. I want us to remember some properties of the dot product. First one, if I take u and I dot it with v, I'm going to end up with the same result as if I took v and dotted it with u. Second property I want us to remember, if I take u and I multiply it by some constant k and I dot that with v, that's the same as if I dotted u with v and then multiplied by that constant k. Next property, if I take u and I dot it with u and I end up with 0, that only happens if u is in fact the 0 vector. Otherwise, u dotted with u is going to be greater than 0. Last property I want us to know, if I take u and I add it to v, and then I dot that with vector w, that's the same as dotting u with w, dotting v with w, and then adding them together. Okay, that is going to lead us to the definition of an inner product. So we say the inner product of two functions f1 and f2 on the interval a to b is the following. Inner product of f1 and f2 is going to be the integral from a to b of f1 of x multiplied by f2 of x dx. So this is how we find the inner product of two functions. The reason we call this an inner product is that this integral, or really any definite integral, is going to have all of these same properties. So the properties for an inner and dot product of vectors is going to be the same for the inner product of two functions. We say that two functions are orthogonal on the interval a to b if, you can probably guess this, what do you think? Two functions are orthogonal if their inner product equals 0. Oh, sorry, I didn't realize I was off the screen. Yeah, 0. Now, something to know. Orthogonal here does not mean perpendicular. There is no geometric significance to being orthogonal, to two functions being orthogonal in this way. So it's a term that you're going to need, but it does not mean that your two functions are perpendicular. First example, if we take f1 of x to be x squared, and we take our second function to be x cubed, and we look at the interval -1 to 1. What we're going to do together is we're going to compute the inner product. So this is going to be the definite integral from -1 to 1. Then you're going to multiply the two, so x squared multiplied by x cubed dx. So this ends up being the integral from -1 to 1 of x to the 5th dx. So this ends up being 1/6 x to the 6th from -1 to 1, which hopefully you can tell is 0. Because we get a an inner product of 0, we can say that those two functions are orthogonal on that interval. Okay, often we are not interested in two functions that are orthogonal. We are interested in a set of functions that are orthogonal. That's what we're going to do for kind of the rest of chapter 11. So we say that a set of functions this set of functions is orthogonal on AB if you find the inner product of any two of them and you get 0. So if I take the inner product of any two functions and I get 0, then we say that the set is orthogonal. Then an orthogonal set of functions is said to be orthonormal if the norm of each of those functions is 1. Okay, you guys have found the norm of vectors before. You're going to find the norm of a function the exact same way. So remember that if you take u and you dot it with u, that's going to be the norm squared, which tells us that the norm of u then is the square root of u dotted with itself. Here then, the norm of any of those functions is going to be the square root of that function dotted with itself, or the inner product of that function with itself.
And the first line, is that VU and then
Should be u.
Then U. Like
This is u.
okay.
Sometimes my u's look like these.
So if you have a set of like a bunch of functions and none of them are orthogonal except 2, then the whole set is orthogonal?
No, every pairwise
Every
match.
pair has to be orthogonal?
Yes. Yeah. So often you're going to have a set that has some common characteristic. You're not just going to have a bunch of random functions. So like here's an example. Show that the set 1 cosine of x, cosine of 2x, etc. is orthogonal on negative pi to pi. Okay, so this is what I mean. You have this random first term, but then everything else is cosine of nx. So ultimately, we need to show that when we take the inner product of any of those two functions, that we're going to get 0 when m does not equal n. So it's saying don't take the inner product of a function with itself. Our first function is 1. Every function after that is cosine of nx, because we're starting n at 0. So first function is 1, every other function is cosine of nx. So ultimately then, two different cases arise. First case we need to consider is if we choose that first function and then another one. So if we choose 1 and any one of the cosines. Second case that we need to consider is when we choose 2 of the cosines.
also just be able to do the one case where n is equal to 0 because the cosine of 0 is just 1.
If one of them is 0, isn't the whole thing orthogonal?
I'm going to say yes, we could write that as cosine of 0x. Okay. So this case then, if we want to calculate this inner product, it's going to be the integral from negative pi to pi of 1 multiplied by cosine of nx. If we integrate that, we get 1 over pi sine of nx from negative pi to pi. Which we can see that case gives us 0. This is the case that we're more interested in. If we calculate this inner product, it's going to be the integral from negative pi to pi of cosine of mx multiplied by cosine of nx dx. And again, we said m and n are different. You're going to have to use a trig formula here. Anyone know what cosine of mx times cosine of nx gives us? Probably not, right? Because you don't use this formula hardly ever. Okay, it gives us 1/2 the integral negative pi to pi of cosine of m plus n x add cosine of m minus n times x. So you are going to use that one either in your homework or the packet, I don't remember. There's also a similar one for sine that you're probably going to have to look up. So if I integrate this then, I get 1/2. Integrating cosine is going to give me sine of m plus n times x, but I'm going to have to divide by m plus n. And then I again get sine times m minus n of x over m minus n from negative pi to pi. If we plug in the pi and the negative pi, we get sine of m plus n times pi over m plus n. Add sine m minus n times pi over m minus n. Subtract sine of m plus n times negative pi for m plus n. Just like that. Subtract sine of m minus n times negative pi. Sorry, I ran out of room. You get the idea. Sine of any multiple of pi is always going to be 0. So this also gives us 0. Margot?
Could we stop after the first case because that's equal to 0?
Has to be any pairwise functions though.
So you have to check everything. Like,
Right. Every single possible pair has to give you 0. Okay, we go on orthogonal sets. Okay, what we are now going to do is we are going to use the orthogonal set from number 2. So the example we just looked at to form an orthonormal set. So again, we have to find the norm of 2 different functions. We need to find the norm of the 1, and then we need to find the norm of cosine. Finding the norm of the 1, we're going to take the square root of the integral from negative pi to pi of 1 dx. So this will be the square root of x from negative pi to pi. So ultimately we're going to end up with the square root of 2 pi. Then if we consider all of the other functions, we're going to get the square root from the integral of negative pi to pi of cosine squared of nx. Hopefully this one you do remember. This is the one with the 1/2. We're going to end up with 1 plus cosine of 2nx. So integrating this, we're going to get x add sine of 2nx over 2n from negative pi to pi. Once we plug in pi, if we plug in pi to sine, we're going to get 0. Plugging in negative pi to sine, we're also going to get 0. So we end up with the square root of pi. So then if we want our orthonormal set, we're going to have to divide all of those functions by the norm. So we get 1 over the square root of 2 pi, cosine of x over the square root of pi, cosine of 2x over the square root of pi, etc. Questions before we keep going on orthogonal or orthonormal? Okay, the rest of the notes is kind of a bunch of definitions. So we're not going to do any more examples. This is going to set us up for the rest of the unit. So here is the ultimate goal later on, so like after break, what we're going to be doing is we want to be able to expand a function in terms of an infinite set of orthogonal functions. So we're going to take some of f of x, some function. We're going to have a constant multiplied by our first function, another constant multiplied by the second function, etc. So C0 and C1 are not necessarily just numeric constants. They could be a function in terms of n. So this is a constant in terms of n, another constant in terms of n. Here are our orthogonal functions. We are going to be interested in finding what those constants are. To do that, we're going to use the inner product. We are going to take the inner product of f of x, so all of that, with each of those orthogonal functions. That'll give us C0 times the inner product of the first function multiplied by this one plus C1, inner product again of now the second function from f of x multiplied by this again, etc. Now, looks like a lot of work, but we do know that on the right-hand side, all of those integrals are going to equal 0 because the functions are orthogonal, except when m equals n. What we get in that case is the integral from a to b of f of x inner product with the nth orthogonal function. That's going to give us c of n multiplied by the inner product of the function with itself. You guys with me? Kind of. We're not doing this section, but I want us to know that this is eventually where we are going. So what we get then is c of n is this integral divided by that one. And this applies to n equals 0, 1, 2, etc. So you would have to do that for each of the functions. Now, when we do this, you will be able to find a pattern of some type. You're not going to do this for literally every single orthogonal function. Here are some other ways that that can be expressed. Or that f of x can be expressed. F of x then is the sum from n equals 0 to infinity of c of n multiplied by each function. And then c of n is all of that. If you don't like having c of n in there, another way to express c of n, the numerator is the inner product of f with each function divided by the norm of that function squared. Okay, we got like three more definitions. You guys got that in you? Okay. Next definition. We say that a set of real valued functions same notation as we had before. That set of functions is orthogonal with respect to, so that's what WRT is, with respect to a weight function which we're going to call Wx on the interval a to b if I'm going to take the definite integral of the inner product, but I'm also going to throw weight in. So I'm going to have weight and then the inner product of any of those two functions if that equals 0. So taking the inner product but then multiplying weight in also. That gives us 0 when m does not equal n. We say that the set of functions is orthogonal with respect to a weight function. You're going to do exactly the same as what we did before. So, is it okay if we don't do an example?
Yes.
Okay, beautiful. Here's the assumption. Is that that weight function has to be greater than 0 on the interval a to b. Okay, so if your set is orthogonal with respect to that weight function, then c of n becomes that same integral or a similar integral. Numerator will be f of x, w of x times each one of those orthogonal functions. Numerator will still be the norm like it was before. Norm this time is multiplied by w of x, though, in the integral. Either series or either Cn is said to be an orthogonal expansion, orthogonal series expansion of F. Other term is a generalized Fourier series. Sections 11.2 and 11.3 are Fourier series. So you'll actually have, we're not going to do it with weight, but you'll have a function, and then you'll have orthogonal functions, and you'll be trying to write your one function as a series of orthogonal functions. Okay, last definition. A set is complete in the class S if that set contains sufficiently many functions so that every function in S can be written in the following form. For a set to be complete, the only function orthogonal to each member of the set is the zero function. Quick vector example. If we consider S to be all vectors in R3, the following will be a complete set. The first vector is the vector 1, 0, 0. Second vector is 0, 1, 0. Third vector is 0, 0, 1. Every vector in R3 can be written as a combination of those three. And again, the only function that is orthogonal to all three, not function, the only vector that would be orthogonal to all three would be the zero vector, hence showing us that this is in fact complete. No, we're not interested in vectors, we're interested in functions, but it's the same idea. Any questions? Yes.
Wait, so I'm still a little confused on complete. How does, like, our example prove that it's complete?
One, you can see it. Second way, so up here, for a set to be complete, the only function, in this case it's going to be the only vector, orthogonal to all three is the zero vector.
Okay.
So there's not a single vector that would be orthogonal to all three at the same time.